Hi there. Welcome once again to our Industrial Electronics and 6 session. I'm Sito Bejane, and in today's session, we'll be continuing with our lesson 2 of RC circuits calculations. Today's example is extracted from example 1.4 from the TVET First textbook by Macmillan and Trope and Publishers. And the example reads as follows. A 50 Hz square wave signal whose voltages are 10 volts high and negative 5 volts low is connected to a series RC circuit with a resistance of 820 ohms and a capacitance of 12 microfarads. Given that the voltage across the capacitor is initially 0 volt, sketch one cycle of the current transient. One cycle of the current transient must include the charging and discharging. Now, what we're looking at here is a signal which is a square wave because of the type of voltage that is given to us, the 10 volt high and 5 volts low. 10 volt high meaning positive and 5 volts low meaning negative. Now, just a rough idea of what is it that you should be looking at here. You must be able to sketch a graph that is like this. That graph should be having this type of a shape. This is the shape that you must be having when you are sketching your graph, like this. Now, here we'll be having two maximum currents at this point here and at that point there. Two maximum current. Now, this two maximum current, we will call this one I1. We can call this one the second current, I2. We'll call this one I3, and then we'll call this one I4, not T, I4. We'll call that I4. So this is roughly what you are looking for. But now, what we have here is a full period of the half cycle, right? This is your period in T, and this is your current in milliamperes. This will be your current in milliamperes. Now, because this is a square wave, and we are given our frequency to be 50 hertz, which means that the whole period of this one cycle, T, would be given by 1 over F. This would be 1 over 50. Now, if it's 1 over 50, your calculator should give you 0.02 seconds. This means here, to complete the half cycle or this one cycle, it will be completed at 0.02 seconds, right? But a quarter of or half of this one cycle here would be 0.01, while here is at 0. So you must be cognizant of these values whenever you're doing your calculations. This is just the rough estimate of what you should be expecting. Now, we need to calculate I1. Remember, I1 is the same as I max because that is the starting point. Now, I1 will be calculated just here, and this would be at t is equal to 0 seconds. Right. Now, at t is equal to 0 seconds, we'll be calculating our I1, which is the same as I max. So this means that I could simply calculate it as V going positive. This is at the positive side, right? So V supply at the positive side divided by R. This should give me 10 divided by 820. And here I will be having 12.2 milliamperes. So the value here would be 12.2 milliamperes, right? Look at it very carefully. Now, the next step that I need to do is to calculate I2. Where will I calculate I2? I2 is situated at 0.01 seconds. right? Now, the value of I2 should be calculated as IS, or I supply, E to the power negative t over time constant. E to the power negative t over time constant, where is the same as I max, which in this case is I1. That is our starting point. Remember, I said your I1 would be your starting point, maximum before going low. I3 would be your starting point, maximum before going high, or rather minimum before going high in that case, right? So what we need to calculate here is our time constant. Our time constant would be given as R times C, 820 multiplied by 12 microfarads, just like that. And uh, that should be able to give us 9.84 milliseconds. 9.84 milliseconds, right? So it is at t is equal to 0.01. So therefore, our I2 would be, like I said, ISE to the power negative t over time constant. When we substitute that, we'll have 12.2 exponent negative 3. Put that in a bracket, and this would be E, sorry, let's do it like this. This would then be E multiplied by E to the power negative 0.01 divided by 9.84 exponent negative 3. You punch that in your calculator. You punch that in your calculator. This would give you 4.41 milliamperes, right? That should be able to give you 4.41 milliamperes. It is the current I2, the current that will flow here. Let me choose a correct eraser here. Now, this would be equal to 4.41 milliamperes, just like that. You see that? Perfect. Now we need to go on and calculate our R3, I3. Remember, I3 would be the maximum current here at the negative side. So we need to first, because at this point now the capacitor will be discharging. If the capacitor would be discharging, it means now we are dealing with the negative 5, which is negative 5 low. But first, we need to find out from the 10 volt which was supplied, how much voltage did the capacitor obtain before we subtract it down? How much voltage did the capacitor obtain before we subtract it down? So this means that we need to first calculate the value or the voltage across the capacitor. Vc would be calculated as Vs into 1 minus e to the power negative t divided by time constant, just like that. Now, the voltage that we need to see how much it is charged through is 10 volts, right? Minus e at t what? We are still at t 0.01. Can you see that? At t 0.01, and our time constant is still 9.84 exponent negative 3. We are still at that point. And we find that the capacitor had charged up to 6.38 volts. The capacitor had charged up to 6.38 volt. Now, this we need, like I said, to consider the low voltage. And just after Vs goes low, Vs will become a negative 5 volt, and Vc would be a 6.38 volts. Right. Which means that our I3 or our IM, sorry, or our negative Im, if I may put it this way, would be calculated as Vs negative minus Vc divided by R, divided by R. Now Vs negative is minus 5 minus 6.38 divided by 820. This should be able to give us negative 13.9 milliamperes. So the current here would be negative 13.9 milliamperes. That is the current that will be present at that point at 0.01. Now remember, I said that will be your maximum or your minimum current before going high, right? Now we need to calculate at this point the value of I4. We need at this point to calculate the value of I4. Like I said, this would become the maximum, right? We use the equation I4 is equal to Is or I maximum e to the power negative t over time constant, where Is is I3, Im to the negative, right? Now, this would be, we insert it like that, as negative as is, it's negative 13.9 exponent negative 3 e to the power negative. Now this is the last 0.01 phase. Can you see that? From here to here is 0.01 current seconds. From here to there is 0.01 seconds. So would use it as is to the power negative 0.01 divided by 9.84 exponent negative 3. When you punch that in your calculator, you should be able to get 5.02 milliamperes, right? So that is the current here, negative 5.02 milliamperes. Now, at this point, you would have completed your one cycle of the charging and discharging diagram. Now, this type of a problem will occur much more than you can imagine in the exam room. First, understand how the diagram should look like, the shape. But basically, this is what the exam question would require us to do for the one cycle of the current transient. First, calculate your I1, which is equivalent to Im, that is your maximum current before going low. In terms of charging, remember, in an RC circuit, when the capacitor is charging going up, the current drops. Hence why we're having the maximum being at 12.2 and the minimum being at 4.41, but we would not charge it fully because we want to see just one cycle. And we've already found out that half of that one cycle would be 0.01 second taken from the 0.02 seconds of the full one cycle of this diagram. And we then calculate the value of I2, given that the value of I1 becomes the maximum current before going low. And then we then move again to find the value of I3, which in this case we need to first find out how much voltage did the capacitor receive before discharging. And at this point we've obtained that the capacitor before discharge had charged 6.38 volts. Now we are going to subtract that 6.38 volts from the negative 5 low voltage. That will be minus 5 minus 6.38 volts divided by the resistance that is present in that circuit. Now, that in this case would give us negative 13.9 milliamperes. That would be your maximum or the lowest current that the capacitor would have discharged or would have charged to before going up, right? Now, the discharge current in this case would be I4, which would be Im multiplied by e to the power negative t over time constant. At this point, I said I3 would be the maximum current or the supplied current before going high that you'd be using. And then, of course, the last thing that you'll be doing is to draw your diagram in this way. That's it for me today, folks. Hope this lesson was informative and exciting. Let us hope to meet again next time for another exciting session of industrial electronics.